Hi, in this video tutorial I'm going to show you how to create a SAP 2000 model of the beam shown here. We are given the modulus of elasticity, the moment of inertia, and also we're told that support C settles downward by 0.2 inches. The objective is to demonstrate how to create this model. A separate video will illustrate how to obtain the deflected shape, support reactions, shear diagram, and the moment diagram. So to start, we select this icon. We have to designate the units for the model. We can select from this drop-down menu. However, keep in mind that regardless of the system of units that you select at the outset, you can always change the units later on in the model, which will be shown down here in the lower right hand corner. For now, we are going to model using kips, feet, and this F represents the temperature in degrees Fahrenheit. I recommend the use of the grid only option. This beam will be modeled on the XZ plane because it is a 2D analysis. Please keep in mind that whenever you use SAP 2000, you must always model a 2D structure on the XZ plane. We must specify the number of grid lines along the X direction, along the Y direction, which points into the screen, and along the Z direction, which is upward. In this beam, we need to specify 1, 2, 3, 4 grid lines along the X direction, only one grid line into the screen, and only one grid line in the Z direction. If you had a frame, you may require additional grid lines in the Z direction. So we specify 4 grid lines in the X direction, 1 in the Y direction, and 1 in the Z direction. The next thing we have to specify here is the grid spacing. According to our model, we have variable grid spacing, 4 feet, 4 feet, 12 feet. Unfortunately, at the outset, the software does not allow us to define these different dimensions. Therefore, since 4 feet shows up twice and 12 feet shows up once, I'm just going to select a typical spacing of 4 feet. However, I can always modify the spacing later. So we're going to specify 4 feet here. In the Y direction, which goes into the board, it doesn't really matter what you specify since you only have one grid. There is technically no spacing, but the program will not allow you to specify 0. The same thing happens in the Z direction, so I just specify 1. This represents the location of the origin for your X, Y, Z coordinate system. The next thing we want to do is we want to specify on this viewport the XZ plane. You can keep this viewport in the 3D view or you can get rid of it. We want to keep in mind that the spacing was 4 feet. What I need to do is we need to modify the grid spacing. To do this, you can double click with the left mouse on the grid and this comes up. Alternatively, you can select Define Coordinate Systems Grids, Global, and say Modify or Show System. Now you can see that we need to specify the ordinates for the X, the Y, and the Z grid data. So this defines the positions of each one of those grid lines. The origin is at 0, grid line B is at 4 feet away from A, C is 8 feet away, and D here is shown as 12. However, the total distance from A to D to this grid line should be 20. So we're going to change this number to 20 and then just hit tab and we're going to say OK. If you had already drawn the structure and then later realized that you needed to make a change, what you would have had to do here is after making this change, you would have to select Glue to Grid Lines. This would have adjusted the grid lines as well as the length of any affected members. The next thing we need to do is to draw our members. We can use this simple tool to draw line elements. We start here and left mouse click all the way across. It looks like we're off the screen here, so I can just scroll down on my wheel mouse to zoom out, or upward to zoom in, and then I can select that. Once I'm done, I hit the escape button, and that is done. Now to see the entire structure, you can just restore the full view like this. We have created 3 segments that go from A to B, B to C, C to D. The next step is to define our boundaries. We have a pin support at A, roller at C, and roller at D. So all we have to do is select this joint, go to Assign Joint Restraints, and then you can use one of these fast restraints. You can select the pin and say Apply, and you can see that the pin was created there. You select this joint, and you can select the roller, hit Apply, and that creates our boundary conditions. Let's assume that you had accidentally defined a roller here, for instance. In order to remove that, what you do is you click on that joint and then you hit this button, which means no restraint, and apply, and it eliminates that. Also, if you define a fixed boundary condition, you notice that this symbol shows up. Now that we're done with this, the next step is to define the material and also the cross-section. If you recall, the modulus of elasticity shall be 29,000 KSI. So this is very easy to do. Just go to Define Materials, and then what we're going to do is we're going to add a new material for this demonstration. I'm going to select Other, and I'm going to call this Mat for Demo, meaning the material for this demonstration. It's important to remember to neglect the self-weight of the elements when you're given the loading, as is the case for this problem. What we need to do is we need to specify a 0 weight per unit volume. Now, this is the modulus of elasticity. We need to convert the units to kips and inches. And you can see that the modulus of elasticity is 29,000. You can leave the other numbers as they are. We hit OK and OK to accept that material definition. Next, we need to define the cross-section. The important thing for this problem is that the moment of inertia shall be 1,000 inches to the fourth. Before we proceed to define the cross-section, we must change the units here to kips and inches, and the reason for that is that we want to specify a moment of inertia in inches to the fourth. Failure to change these units will introduce a unit error. So the next thing we do is we define section properties, frame sections, and what I'm going to do is I'm going to add a new property. These are different types of cross-section configurations that are typical of steel members, of concrete members, etc. You can use any of these. So for example, you can specify a solid rectangular section with appropriate dimensions to give you the desired moment of inertia. However, there's an easy way to define a general section where you can enter all the properties that you want. So for example, we need to define a moment of inertia of 1,000 inches to the fourth. The moment of inertia about the 3-axis is the desired one. So you specify 1,000 inches to the fourth. If you're confused by this, you can always specify both of them as 1,000, but since this is a 2D analysis, the 3 direction always corresponds to the bending direction of the beam. So in general, the 1 dimension is axial, the 2 dimension is in the direction of the shear, and the 3 dimension is in the direction of the moment. These correspond to the local axes of the element. So 1 for axial, 2 for shear, 3 for moment. We say OK, and let's give this a name. We can call it beam, or I can call it EI, for example, because that represents the flexural rigidity that is assigned to this section. Before we go on, we must attach the material here to this cross-section. Furthermore, there's a button here that corresponds to property modifiers. Think of these as scaling factors. For example, this number here scales the cross-sectional area of the element. There is a shear area scale factor and other scale factors as shown here. It's important to recognize what type of analysis you want to perform. So if you were to use this calculation from SAP to confirm a hand calculation, typically hand calculations do not include axial deformations or shear deformations. In order to neglect axial deformations, you need to make this term large. You may recall delta, which is the axial deformation, is PL over AE. P is the axial force that develops in the element. L is the length of the element divided by A, which is the cross-sectional area, and then E is also in the denominator. So the axial deformation is PL over AE. You cannot change the axial force that develops. The length is specified, and the E is Young's modulus. Therefore, by increasing the cross-sectional area in the denominator, you're reducing the axial deformation effects. It is customary to specify something along the lines of 10,000 or 100,000 here. Similarly, if you make this multiplier large, such as 10,000 for the shear area in the two direction, you're neglecting shear deformations. So as shown here, we are neglecting both the axial deformation and the shear deformation. We can also specify a multiplier of 0 for the weight and mass, just to ensure that there is no self-weight accounted for in the model. Hit OK. At this point, it might be a good idea to save our model. I'll call that beam. Next, we need to assign the properties that we just defined, assign them to these elements. So we select all the elements and we say assign frame sections, and then we select EI, which is the section that I defined, say apply and close. You can always go back and verify what sections have been assigned by clicking this icon here, which defines things that you want to observe for joints and frames and other types of elements. So for example, if you want to see the section labels for the frames, the sections that apply, you hit that and you can see EI, EI, EI. Now you can remove that, and now it's nice and clean. Next, I'd like to show you how to model the loads. So we have a point load at B and a uniformly distributed load of 3 kips per foot between C and D. The 10 kip load acts downward at B. So let's model that one first. Select the joint, go to Assign, Joint Loads, Forces. These are the forces in the X direction, in the Y direction, and the Z direction, and these are local moments. So if you wanted to apply a moment in a particular direction, you would do that here. Typically, for a 2D analysis, you would be applying, for example, horizontal forces, that would be here, vertical forces would be here, and moments, they would be here. Recognizing that the Y direction goes into the board, so a positive value would represent a clockwise moment. So today we have a vertical force of 10 kips downward. So what we do is we apply a negative 10 to represent that load acting downward. Next, I'd like to show you how to define the uniformly distributed load of 3 kips per foot. Notice that the units here are kips and inches. Let's convert that to kips and feet. You select the element this time because the uniformly distributed load acts over the element. It's an element load. So you assign frame loads distributed, and since we have a uniformly distributed load, we can just specify here 3 kips per foot. We don't have to specify a negative because the loading direction has already been specified here as the gravity direction. When you model in SAP, the gravity direction is always downward along the Z direction. These fields here are used if you want to model, for example, a triangular loading pattern or a trapezoidal loading pattern. So it looks like we lost our point load here. However, if you study this carefully, it says frame distributed loads. So what it's showing us right now is only the distributed loads. There is a way to display the loads that have been defined. So that shows all of the loading. Before you run the analysis, we have to select Analyze, Set Analysis Options, and then select this button here, which represents a planar analysis. What you're doing is you're removing all the degrees of freedom associated with torsion and displacements out of the plane of the screen. You hit OK, save the model. The last thing we have to include is the effect of support settlements. So we have here that support C settles down by 0.2 inches. In order to model that, what you do is select the joint. I'm going to change the units here to kips and inches. And I'm going to say assign joint loads displacements. So this is how you define the support settlements. You can model any type of translation or rotation here. In our problem, we need to specify a downward displacement of 0.2 inches. So we need to specify that as a negative value. And you can see the direction indicated here. Now we can save our model, and the model is ready to be run. In the next video, I will show you how to run the model and then how to post-process the results. Thanks for watching.